All right, subscribers, welcome back to another episode of Science with Surback. In today's episode, what we're going to be talking about is AP Chemistry section 15.7. This is the final section of notes on our equilibrium unit. So, with our equilibrium unit, section 7, before we get going, I just want to outline a couple objectives. And number 1, you need to be able to, by the end of this lesson, state Le Chatelier's principle, explain how the equilibrium quantities of reactants and products are shifted by changes in temperature, pressure, or their concentrations. Number 3, explain how the enthalpy of a reaction is determined and the change in the value of an equilibrium constant when temperature is changed. And then the fourth thing here, describe the effect of a catalyst on a system at equilibrium. So we start out here with this principle of Le Chatelier's. And so Le Chatelier's principle states that if a system is at equilibrium and it's disturbed by a change in temperature, pressure, or a component concentration, it will determine, or we will determine, the shift in the equilibrium so that it is corrected after this disturbance. So let me write that down, and then we'll explain more of that in a second. All right, so kind of a lengthy definition here, but what it's saying is that if we have an equilibrium system, so the equilibrium system, it's already came to equilibrium, if we alter anything, it is going to adjust what happens to that equilibrium. So there's 3 main changes that we in this class are going to concentrate on, and we're going to define these changes and tell you what happens, and then we'll apply them in a couple of examples later on. So number 1, we have a change in concentration. So if we increase a component, or we increase the concentration, the equilibrium will shift towards the opposite side. And if, for whatever reason, we have a decrease in concentration, the shift is going to occur to that same side. So it's kind of hard to see here by just looking at these definitions, but when we go through the examples, this increase or decrease business and predicting which way the shift will occur will seem a lot simpler. Now, a lot of our equilibrium systems have occurred with the unit of atmospheres or the unit of pressure. So if there is an increase in pressure, the equilibrium is going to shift toward the side with the least number of moles of gas. So let me pause and write that down. All right, so there is that increase in pressure. And now one thing I haven't made clear here, when we talk about shift, we're talking about either the forward or reverse reaction occurs. Now, if there's a decrease in pressure, the equilibrium is going to shift towards the side with the most number of moles of gas. Again, here, with this shift, we're talking about what side or what type of reaction, the forward or reverse reaction, needs to occur. And these shifts will seem a lot easier once we get to our examples. Now, if there is a change in temperature, number one, we have to know the enthalpy of the reaction, which will be given. But if there is an increase in temperature, the equilibrium is going to shift towards the side that does not require heat. All right, so there it is. Increase in temp, the equilibrium shifts to the side that does not require heat. Now, if the temperature decreases, the equilibrium is going to shift toward the side that does require heat. All right, so there is that written portion of what happens to the equilibrium when we decrease in our temperature. Now, we get to this bottom portion here, and we have to talk about the catalyst's effect on equilibrium. So number one, a catalyst does not affect the composition of the equilibrium mixture, and it's not going to shift the equilibrium one way or the other. All that's going to help with a catalyst involved experiment here is that equilibrium is just going to be achieved at a faster pace. So let me write that down. All right, so those two things here, what happens with a catalyst. Again, it does not affect the equilibrium composition. It just gets to the point of equilibrium a lot quicker. All right, so this is a lot of definition, and it's probably hard to wrap our mind around what this Le Chatelier's principle is and how this effect is going to shift the equilibrium equation. So what I have here on the next 2 pages are some examples. And so we will go through each of those things that we talked about in that notes on the first page. So the first thing is this. We are going to use this equilibrium equation that we have here, and we're going to say which way the equilibrium shifts, either left or right, depending on what we do in these scenarios. So the first thing that we have here is that we have an increase in each of these substances. So if you remember, if we increase the concentration or the amount of any substance at equilibrium, it will shift to the opposite side. So let's go ahead and let's take N2. If we increase, we put more N2 into this equilibrium, what happens is it shifts to the opposite side. So that means in this scenario, it will shift to the right. Now, if we increase H2, again, H2 is over here. If we increase it, the equilibrium shifts to that opposite side. So if we increase H2, again, the equilibrium is going to shift to the right. Now we have NH3. Again, we are increasing our NH3. So NH3 is over here, and if we increase NH3, the equilibrium shifts to the opposite direction, so that means it shifts over here to the left. Now, down below here, it says a decrease in these particular components. So if you look back on page 1, a decrease of any component or concentration will shift the equilibrium to that same side of the equation. So we start again here with a decrease of N2. N2 is over here on the left. If we decrease it, it shifts to the same side. So because it's on the left, it is going to shift to the left. Now H2, we decrease it. Again, by definition, a decrease shifts it to the same side of the equation. So because H2 is on the left and we decrease it, it is going to be shifting left. Now NH3 is over here on the right. If we decrease the amount of NH3, the equilibrium will shift to that same side. So that means for this value here, it is going to shift to the right. Now, our change in pressure, we got to do a little bit of work to obtain the value or obtain what way the equilibrium shifts. So if we increase pressure, the definition on the first page said it shifted, the equilibrium shifted to the side with the least number of moles of gas. So before we answer these two questions, what we need to do is we need to count the total number of moles of gas in this particular equilibrium expression. So we look over here on the left. The coefficient tells us how many moles of that particular substance we have. Now, all of these substances are gases, and so for N2, that means we have 1 mole of N2 gas. We also, over here on the left, have 3 moles of H2 gas. So that means total, over here on the left, we have 4 moles of gas. Now, over here on the right, we have a 2 coefficient. This NH3 is a gas. So total, over here on the right, we have 2 moles of gas. So if we increase pressure, the equilibrium shifts to the side with the least number of moles of gas. Because this right-hand side has 2 moles of gas, or the fewest moles of gas, and we increase pressure, the equilibrium will shift to the right. Now, if we decrease pressure, by definition, the equilibrium shifts to the side with the most number of moles of gas. And again, because this left side has the most number of moles of gas, it's going to shift to that left-hand side. So we've gone through quite a few examples. The temperature, business, or change in enthalpy we haven't gone over. We'll do that in the next one, and then we'll put it all together with a big final problem. So I'm going to get that second sheet of paper out, and we're going to go over to example number 2. All right, so one thing that wasn't talked about in that first example was what happens when we have heat. How does that affect the equilibrium? So before we even get into the details of this example, I want to put one thing up top here at the margins. If something is endothermic, this means that we have a positive delta H, a positive number, and what this means for us talking about equilibrium is that the heat is on the reactant side. Now, if something here is exothermic, that means that we have a negative delta H, and this means we can consider heat to be on the product side. Now, we can't say these things are reactants or products because they're not, but we can consider them to be on one particular side, either the reactants or the products. So we go down to our example here. We have everything that's listed in our particular example, and then over here, most importantly for this one, this example is that delta H is greater than 0. Well, that means delta H is positive. So if we go up here to our little cheat sheet, we can say heat is on the reactant side. So what I'm going to do to make life a lot easier, again, heat is not considered a reactant, but we can say heat is required on that reactant side. This will help out over here. So if we increase the temperature, the equilibrium problems or the equilibrium statements that we went over last page said if heat is increased, the equilibrium will shift to the opposite side that needs heat. So because heat is over here on the left and we increase heat, it shifts to the opposite side, which means this will shift to the right. Now, if there's a decrease in temperature, the equilibrium shifts to the same side that requires heat. Heat is over here on the left. Because we have a decrease, that means the equilibrium will shift to the left. All right, so we know about heat, we know about adding concentration and taking away concentration, and the effect of pressure. So we can piece this all together in this third and final example. So in this third and final example, we have this. We want to know which way the equilibrium is shifted based on these constraints. So the first thing that we start out with is we start out by adding N2O4. Now here, the equilibrium shifts to the opposite side in which it was added. So because N2O4 is on the left, this will cause the equilibrium to shift to the left. I'm sorry, it's on the left, so it will shift to the right. Now, NO2 is removed. If you take things away or you take a concentration of something away, it shifts to the same side that it is on. So because it is on the right, it will shift to the right. Now, over here it says the pressure is increased by the addition of N2 gas. Now, don't consider N2 gas into the equilibrium. Consider an increase of pressure. So to find out an increase of pressure, we need to consider the total number of moles of gas on each side. So over here on the left, there is a 1 coefficient. So that means there is 1 mole of gas. Over here on the right, there is 2 moles or a 2 coefficient. So that means we have 2 moles of gas. If the pressure is increased, it will shift to the side with the least number of moles of gas. So because the most moles of gas is over here, it's going to shift over here to the left. Now, the volume is increased. The volume being increased, this is a fancy way, and I'm going to write this out to the side. This is a fancy way for saying pressure is decreased. So if pressure is decreased, the equilibrium will shift to the side with the most moles of gas, and the side with the most moles of gas is this right-hand side. So it shifts to that right-hand side. Now we have the temperature. So before we even talk about the temperature being increased or decreased, we look at this value for delta H. Now this is a positive value or an endothermic enthalpy change. So if you remember up to the top, an endothermic, we can consider heat to be on the reactant side. It's not a reactant, but we can consider it to be on that particular side. So if the temperature is decreased, we look over here, the temperature is decreased, the equilibrium in a decrease of temperature shifts to the same side that heat is required. So since heat is required on the left, we decrease that temperature, the equilibrium shifts to left. All right, that's all of sections 15.7. That's all of the equilibrium unit. I hope you've enjoyed, and as always, make sure you subscribe.